Okay, cool. Yeah, so I'm gonna tell you a little bit about some work we've been doing on my team at Google Research on sort of deep learning and using deep learning for improving simulations, particularly towards the work we're doing now on sort of weather and climate modeling. Um, okay, so kind of the framing that we have sort of like the place where I'm at Google, we're really thinking about like how we can use Google's technology, which is especially tools like deep learning, which is now really pervasive, of course, in like the tech industry, and basically is sort of going into almost every single product say that Google does. And we're wondering how we can use AI technology for science. We've been focused particularly on sort of computational science. Um, so it's kind of the thesis, the sort of broader thesis that we've been exploring is how this sort of the technology of sort of AI technology, like deep learning tools, particularly deep learning software and this sort of software paradigm can be relevant for computational science. And if you kind of look at what these like deep learning tools actually do, I think there's a lot there that's pretty exciting. And it's not just the sort of the traditional like AI part, which is what people talk about like neural networks, which yes are sort of fantastic models, but for science you need a lot more. But interestingly, sort of the tools, the sort of the key components of deep learning software actually fit a lot of these scientific computing use cases too very well. So I think kind of maybe four key ingredients that we have in sort of deep learning software. So we have the ability to like build these like neural network models, which are like really powerful machine learning models. You can do all sorts of crazy things for like say for understanding language or pictures, but also any sort of complex signals. Very flexible machine learning tools. And these neural networks need a lot of sort of huge amounts of compute in order to train. So they run on typically run these days on accelerator hardware like GPUs or TPUs. And so they can use a lot. They like really efficiently make use of a lot of flops, and the deep learning software makes it really easy to write code that scales to a lot of machines as well. And that of course is also useful for science. Fundamentally, these deep learning tools are libraries for implementing for doing automatic differentiation. So they do gradient-based optimization of everything. Of course, that's also tremendously useful for science. That's kind of like actually originally automatic differentiation was developed for applications like data simulation and weather forecasting for implementing like the adjoint state method. And of course, they're also sort of based fundamentally on doing as like tools for doing scientific computing. And sort of all these sort of popular sort of like deep learning frameworks like TensorFlow, PyTorch, JAX write code that looks very similar to the sort of code that we'd write for science as well, and at a pretty high level in languages like in Python. Okay, so and in particular, I think the particular angle that I think is sort of most exciting within sort of using sort of these deep learning tools is this paradigm of differentiable programming. And this is a notion that you can write flexible computer programs with a bunch of parameters, like for example, the weights of a neural network. Yet you still have some components which look like some other sort of algorithm that like you design, say, by hand, based on some sort of knowledge of sort of the right structure of your problem domain. And you can optimize the entire thing together for some end-to-end objective. So in the case of sort of scientific computing, we can combine together like numerical methods, which we understand well, and they can build all sorts of nice guarantees. We can do things like solving equations. We can combine those we can sort of integrate those in sort of really arbitrary ways with neural nets. And this is pretty powerful because now we have a machine learning paradigm that doesn't require us to go all in on machine learning. It doesn't require us to sort of throw out our existing models. As long as we have our numerical methods written in a compatible way, which is a big caveat, we can optimize these things together, which is really powerful. Of course, the caveat is that our simulations need to be differentiable in order to optimize through them collectively, and it still can be some tricky business to sort of optimize these collective programs, but we can do some really remarkable things if we have these differentiable simulations. And generally, sort of writing things in an auto-diff framework and writing things in deep learning software gets us kind of most of the way there. And of course, a lot of I mean, well, at least a handful of sort of weather and climate codes already kind of are differentiable in some sense, like the ECWF model, which is differentiable for doing data assimilation. Okay, so I'm going to talk about briefly about about some of our prior work on sort of what we've done for sort of computational fluid dynamics with sort of 2D fluids. Then I'm going to get into what we're working on now a little bit, tell you a little bit about what we're currently doing with sort of global weather prediction, and then touch briefly on some sort of unresolved challenges, I think, sort of more broadly for this field. And I'd love to, hopefully we'll have a bit of time for discussion as well. So first, what we've done on computational fluid dynamics. So again, sort of our approach is that we wanted to, I guess, get some experience sort of building things up kind of from scratch. And so we wrote this library we called it JAX CFD. And the key aspects here is, again, because we wrote this in a deep learning framework, we wrote this in JAX, is that we were able to, we kind of built this from the ground up with an eye towards making it something that we could plug deep learning tools into. We wrote it in the deep learning framework, so it's differentiable. It runs efficiently on GPUs and TPUs. We can explore a lot of interesting sort of hybrid machine learning and physics models, like the approach we use here. Actually, in this work I'll tell you about was just learning interpolation operators. So it turns out that interpolation is kind of one of the key, I guess, it's like one of the tricks in in computational fluid dynamics. You have quantities, say, at the center of a grid cell, you need to move to the side of a grid cell. That interpolation looks a little bit like a super resolution operator. It's something that machine learning does pretty well. It's one little teeny bit. We're not trying to ask machine learning to do some crazy, predict the evolution of some turbulent field for far into the future. It's just do one little interpolation step, but repeat that a bunch of times, and you can actually make these codes a lot better. And we stuck with, again, partly because we wrote this from scratch, we stuck with relatively simple numerics. And we think that's also kind of a key thing to this, these sort of hybrid models, is you don't necessarily need the fanciest numerical methods, which sort of with all the bells and whistles, even just very simple stuff can get you a long way, with sort of giving you some of the physics-based inductive biases. Okay, so the approach we did, sort of our general approach here was that we sort of used a simulator to generate some very high resolution simulations of a 2D fluid. And then we're going to try to downsample to a very coarse grid, which is going to be which we can simulate very quickly, but not very accurately with traditional solvers. And then we're going to optimize some parameters in our sort of differentiable solver in order to sort of try to match the evolution of this trajectory on a very coarse grid at a resolution that we could not do with our sort of baseline solver. And so we do it with we have a convolutional neural net, which generates, in this case, it's picking interpolation weights at each point. You could also have something, we've had models that are doing things like learning like a closure term, that sort of a little correction sort of to each state, but it's still running the fluid solver as well. It's just sort of tweaking things a little bit in each step with machine learning. Okay, so when we do this sort of thing, we're able to, improving over these finite volume methods, we can get simulations that run a lot that are sort of accurate on sort of remarkably coarser grids. So here we have a data set where we train things on a 2000 by 2000 grid we used for the baseline for the simulation that made the I'll turn on my laser pointer. Okay. So for our so we started things. Our ground truth is on 2000 by 2000 simulation. If you run that on, say, a very coarse grid, a 64 by 64 simulation, it very quickly loses these vortices get washed out very quickly because the simulator can't resolve them. If you use our sort of, like in this case, our learning interpolation method, it can keep track of things for much longer. And here it's doing something like effectively a 10x higher resolution in space, in each spatial dimension and in time. So that works out to something that is potentially a lot faster as well, of course, because the machine learning models are expensive, but we can because we can run things accurately on much coarser grids. In this case, it's like something like an 80 times faster sort of wall clock time when we run this on like a GPU or a TPU. So that's kind of on the focus of this paper. Of course, and the other interesting thing is, I mean, we test. So because we sort of build into physics, we can do interesting types of generalization tests as well that sort of change, say, the size of the domain, or the sort of the forcing, or even like the Reynolds number. We can still, our model still, the model that we train on one sort of turbulence actually still works reasonably well in the other sorts of turbulence as well. So that's pretty exciting. And I think that's one of the virtues over these sort of more pure machine learning models. Is because we have more of the physics structure sort of baked in, we can kind of have more hopes of generalization. So since then, that work, we've done some work sort of trying to improve spectral solvers for fluids. This is kind of a harder problem in part because spectral solvers, at least for these sort of really sort of 2D fluids with periodic boundary conditions, are sort of tremendous, or like sort of really hard to beat, honestly. Because they can, like, the accuracy converges sort of extremely quickly. But we can still make some improvements with some of our machine learning models. That's kind of on this plot here, sort of showing that we can do things like roughly sort of half, sort of effectively half the resolution. We can sort of achieve sort of similar sorts of accuracy with some of our machine learning models. And I mean, and again, like looking at these, I mean, in terms of the advantages of these sort of hybrid models versus sort of pure machine learning approaches, I mean, the machine learning approaches, I think, can actually be remarkably accurate as well, especially in cases where simulation cases where you can generate arbitrary amounts of data. So it's not entirely clear to me, to be honest, exactly. Well, I think that I mean, we expect that we should be able to see more generalization with hybrid methods. We find generally they are much easier, sort of faster to train. If you look at these loss curves, our hybrid methods achieve the loss sort of much faster. Sort of in this case, it's like something like they're hitting the same sort of loss values, something like 30 times faster than these sort of pure machine learning models. But some of these pure machine learning models actually still achieve a pretty accurate result at the end of the day. I will say that all these models this kind of touches on sort of one of our issues, which is that we often find ourselves training for objectives that are not quite the same thing as what we actually care about from an evaluation perspective. So we might train, say, a model over 30 time steps and try to test it over 1,000 time steps. And we still don't really have a sort of 100% recipe for guaranteeing that that's successful. And we find that the hybrid models tend to sort of generalize. They tend to work better than like the pure machine learning models. They tend to be more stable, but sometimes you get really weird stuff, like the model sort of the performance suddenly drops off, and that's, I guess, kind of a hazard of these sort of machine learning loops where you're sort of optimizing for sort of particular behavior. And sometimes there is sort of a trade-off, I think, between especially as you add more and more machine learning, is that you have more and more risk of overfitting. Okay, I'm going to get into some of the stuff we're doing now and weather. I see I'm 15 minutes in, so I don't want some time to talk about this. Okay, so we're looking now. We've recently, just in the past year or so, we've been looking into sort of into using these techniques on global weather forecasting, and so in the context of writing a sort of differentiable atmospheric general circulation model. And again, the general approach of GCMs, I'm sure most of you are quite familiar with this. You have there's the dynamics, which is just fluid equations, and there's all the physics that happens inside each grid cell and is independent in each vertical column. And so we want to kind of keep this structure in our sort of hybrid-based machine learning method. So we've rewritten we have a prone equation solver that we wrote. As you'll see, we actually did a spectral method. because that was kind of the simplest approach. And we're going to try replacing the physics with machine learning. You could imagine building some of the physics components in, but what we've been doing so far is just replacing this all with a neural net. And again, at a high level, if you kind of look from like a code structure of like what happens in a standard weather or climate model, is that we sort of start with observations. They get sort of mapped via data assimilation sort of into a model. That model sort of simultaneously does sort of solves dynamics and solves physics inside each time step. These contributions get added together, unrolled for some very large number, potentially hundreds in the cases of weather models, or probably thousands or tens of thousands or hundreds of thousands of steps, maybe more for a climate model. And then the outputs get sort of post-processed, things like bias correction that kind of happens at the end. And so we want to emulate this whole process with our machine learning model. And of course, these systems are incredibly complicated. There's a whole lot of, especially in like the physics stuff, a whole lot of stuff going on. What we currently have, I'll show you. So kind of take all the same components, except that we sort of replace every little bit, all the hard bits with something involving neural nets. So we call say an encoder model that goes from observations into the model state. We have what we call say a corrector model that does the equivalent of the model physics. We have a decoder that does the equivalent of post-processing. And again, because we're sort of building this on top of we still building this on top of a dynamical core. In our case, a pretty simple dynamical core we wrote ourselves with sort of a spectral solver. And we're currently using sort of just ERA 5 data observations, but we can so we can build this thing that works kind of end to end. We can optimize. We can use sort of a single column machine learning, sort of relative simple neural net. There's similar to a lot of prior work in terms of sort of learning the full physics here. It turns out that the black box neural net does actually work reasonably well if you unroll your forecasts for up to like a few days. You can make this model stable. And then kind of we have we use sort of like little neural nets to kind of help fix some of these, say the transitioning between different observations of model state, for example, with machine learning, kind of a sort of flexible glue to kind of make everything kind of work reasonably well together. And we can do that because we optimize the whole thing for end-to-end performance. Let me show you a little bit about what some of our early results look like. I don't have sort of comprehensive evaluation yet because we're still kind of working on getting this all together, but just to kind of show you that it's not complete vaporware. This is an example here on the right of our model running at our learned model, giving I think a 5-day forecast at TD5 resolution, which is I guess like something like a 1.5 degrees. So not quite to the resolution of sort of the full resolution we'd like, but we can like say our model, which is emulating the full atmosphere and sort of really is running a full atmospheric simulation, can actually learn. I mean, there's the dynamics, of course, and then it's like learning things like the diurnal cycle. It's a start. We're still working on kind of scaling this up and sort of comprehensively evaluating this. As a side note, I'll say that machine learning hardware actually turns out to be a great way to write some of these solvers, these traditional, especially spectral methods like what ECMWF uses. That's because by happy coincidence, the main operation in a spectral solver is matrix multiplication, which is exactly what the machine learning hardware is designed to do. So we get like 50% flop utilization, which is kind of unheard of. That's like the very best machine learning models can do that. So this is like effectively, these are like machines that are coincidentally like almost like sort of really fantastic fit for writing some of these solvers. So in principle, we can do fairly high simulations even on a single machine. This is like resolution similar to ERA 5 that runs in a few minutes on these machines. Okay, I'll briefly touch on some current challenges, then I'll maybe hopefully have a minute to ask for some questions. I'll just kind of go through these and maybe dive in where people are interested. So I'll say, first challenge, numerical stability, super hard. I think in general, for writing new numerical methods, it's hard to guarantee they're stable. It's worse with machine learning because with the machine learning now you have a really complicated system. You don't understand how it works. And when things go wrong, like this is some early sort of machine learning PDE models we had. When suddenly things go wrong, they go really, really wrong really fast. And we don't really know how to solve this still. I mean, there's a lot of things that people have done to try to do this, but kind of one of the dirty secrets of this field is that lots of these machine learning models are not stable when you ask them to make predictions over long periods of time. They're not sort of they sort of work. There's like a whole graveyard of projects where people have tried to get models that they never quite manage to get stable, which is kind of a shame. And like being able to unroll over time when you're computing losses is helpful, but it's not enough. And so there's a bunch of things. I think this is kind of an unsolved problem, but I'd love, if people have ideas about this, I'd love to hear them. Briefly, there's kind of this challenge about, we have chaotic dynamical systems, and a lot of work people still been we optimize these for like an L2 loss, which is kind of it's kind of an ill-posed problem when you if you slightly get perturbed and put on a totally different trajectory, like doing the gradient-based optimization is like it's not going to help you. It's really not going to work right. And it's kind of sort of, and so there's this nice paper some of my colleagues at Google wrote on that you can read about some of these issues. But fundamentally, I don't think we really know how to solve this either. But I will say that I think we need to do good weather and climate models. And I think part of the solution is probably doing stochastic modeling, because stochastic modeling can kind of average over different scenarios and still make the gradients well posed. But that's a much harder problem than learning deterministic models. Okay, last challenge, of course, these models are incredibly complicated for weather and climate models. If you look at IFS or other types, like say like weather and climate models, I mean, like easily like millions of lines of code. And that's sort of quite the challenge to try to replace, especially if you want to kind of keep around the structure of existing models. That's a lot of stuff to rewrite. So what can we do about this? Well, maybe you can replace, do what NVIDIA does, replace the whole, is trying to like replace the whole thing with machine learning. That seems like, I'm not sure how well it's going to work in terms of sort of some of these generalization concerns. We can maybe put machine learning into the existing codes. I think that's also going to be hard to do because you can't optimize the whole thing together. And I guess short of that, we'll need some sort of large scale community efforts to figure out how to sort of port existing methods to make them differentiable. Okay, and that's pretty much it. So in summary, I want to thank I've got a bunch of great colleagues at Google who I did this stuff with. Yeah, sort of excited to be able to share this stuff hopefully in the near future with everyone.